So the sampling distribution, I think I made it pretty clear what that is in my video of the slides for the Chapter 7 presentation. The sampling distribution is the distribution of all possible values of the sample mean from many, many samples. And I took a screenshot from one video in the second little animated video, and I put the screenshot in your to-do list, so you could check out that screenshot. I want to see if I can pull that over here. Probably not. Let me see. Oh, look at that. I can bring it into the video. So this is, let me get out of that. This is a distribution of all the possible sample means. If you did sample means over and over again from the fish in the sea in that video, then these are the different results you could possibly get. Each little box represents a different sample mean from a different sample. And again, I'm referencing, the screenshot is out of this second video with the little fish in the sea. So yeah, that's the one I was kind of pointing out when I said fish in the sea. So that's the sampling distribution of all possible sample means from many, many samples. The sample mean is a statistic. It comes from taking a sample and finding the mean, okay? The population mean is a parameter. Remember, we talked about this in Chapter 1. It is a characteristic of the population, and unless you have access to Zeus or Thor or whatever that god was, again, I'm referencing that video, you do not know the population mean. We wish we knew it, but we don't know it unless we have a complete census of all the individuals in the population. Now, the central limit theorem has two different conditions. The population must either be normally distributed, or we must meet one of two conditions. So either the population is normally distributed or the sample size is 30 or greater. And I've heard teachers argue about this, but for the purposes of this book, we'll just go with this rule. I don't know if this is universally accepted. I've had people argue with me on that, but anyway, we'll just go with it for this course. When either of these conditions are met, then we can have the central limit theorem, which states that x bar is distributed normally with a mean of mu and a standard deviation equal to sigma over root n. So what this means is that the sigma for x bar is the original population sigma divided by the square root of n. And that's why this goes into this second slot of our normal distribution. And this is saying the same thing again. So one of the examples in my slideshow showed us that x is equal to the height of a child in inches. And this is referencing an experiment that I do with my in-person students where we put a bunch of little numbers in cups. They're on little laminated cards, and each cup has a whole bunch of little numbers in it, and those numbers represent student or child heights, and the x values, the heights, are distributed normally with a mean of 50 and a standard deviation of 4. And then we use samples of size 10. So what I did was I had each student put their hand in the cup and pull out 10 little chips and then find the sample mean from those 10 chips, and then they would put them back, and then they would get a sample mean again and again. And so we did a lot of sampling out of those little cups, which represented the population of the students, the children. Why can we apply the central limit theorem here? Which of the conditions was met? Because the children's heights were normally distributed, it didn't matter that our sample size was just 10. And again, obviously a sample of size 10 is pretty small. I was just trying to make this activity not terribly cumbersome. So we had X being distributed normally with a mean of 50 and a standard deviation of 4. And now we have the distribution of X bar. X bar is distributed normally with a mean of 50, and the standard deviation is 4 divided by the square root of 10. So you can see I'm just applying what was given up there. 4 divided by the square root of 10 is 1.26, and that makes me wish I had my calculator pulled up here. Again, 4 divided by second square root 10 should give you that result. And then what is the probability that X is between 46 and 54? And I purposely set that up to be exactly 1 standard deviation below the mean and 1 standard deviation above the mean. Notice that we're talking about X, the student height, and so you shouldn't be surprised to see the result of 0.68. We go to second distribution, normal CDF, lower, upper, mu, and then sigma, and that gets us our 0.68. And then what is the probability that the sample mean is between 46 and 54? So notice that these are two different questions. One is asking, what is the probability that, let me put this here, that a child's height is between 46 and 54 inches, and then this question is that what is the probability that the sample mean is between 46 and 54 inches? So you can see that here we get 68%, and then when we repeat that process, we still say lower, upper, mean, and then the only thing that really changed is right here, because now we're talking about the sample means, so we change our sigma to 4 divided by the square root of 10, and we get 99% likelihood. The sample mean is 50, so it's 99% likely that our the population mean is 50, so 99% chance of the sample mean landing between 46 and 54. It's not going to be, we're not going to get a sample mean of like 40 inches. We're going to get kind of close to 50, so I'm not surprised that that was 99.84%. And then down here, I'm just explaining the difference between my answers in 4 and 5. 68% of the children have heights between 46 and 54. This is what I just said. The sample means are always going to be closer to the population mean. That shouldn't be too surprising.